Hello everyone, I'm L.G.R.I Samarawickrama from the Department of Geography and International Center for Multidisciplinary Studies, Faculty of Humanities and Social Sciences, University of Jayewardenepura. Research topic is titled Rainfall-Induced Landslide Triggers During Cyclone Ditwah in Sri Lanka's Central Highlands, a GIS-based intensity duration threshold analysis. Here, I have mentioned the authors who contributed to this research. According to the introduction part, I would like to first introduce the event Cyclone Ditwah. Actually, Cyclone Ditwah was a severe tropical cyclone that struck Sri Lanka in November 2025, and it was delivering prolonged high-intensity rainfall. The main impact of this cyclone is it was generated intense rainfall and strong winds, leading to environmental and socio-economic impacts across several regions. As well as the mountainous and low-lying areas experience significant hydrological and geomorphological hazards, including floods, landslides, and slope failings. Then, how Ditwah affected to trigger landslides? Actually, with the extreme precipitation, it overwhelms soil infiltration capacity. Intense and prolonged rainfall is the primary trigger for landslides in tropical mountainous regions. The mechanism behind this is extreme precipitation exceeds the natural drainage capacity of steep slope, and subsurface water accumulation elevates pore water pressure, drastically reducing effective stress. The failure occurs when soil shear strength is finally surfaced by this internal pressure. Here is the problem statement and the knowledge gap. We have found the current limitations as early warning systems rely heavily on multi-event regional datasets that average out monsoonal and frontal rain. And the gap that have identified is generalized regional models fails to capture temporal concentration during extreme cyclones, and actually there's no quantitative site-specific threshold currently exists for Sri Lanka. So that's a novelty of this research. And this research generates a power low rainfall threshold model to present the relationship between rainfall intensity and duration. Here is the significance of the research. Identify rainfall threshold and spatial landslide cluster can support safer settlement planning, infrastructure development, road network management, watershed conservations. Not only that, this study contributes to climate resilient development by linking scientific hazard assessment with practical making for vulnerable communities and local authorities. Here is the objectives that we mainly focused in this research. One is to determine the perceived rainfall threshold for landslide initiation during Cyclone Ditwah. Then to analyze the rainfall by using GIS-based data to identify the peak rainfall. Then to model threshold value to derive empirical intensity duration relationships specific to cyclone. After, as the final objective, to utilize GIS overlay analysis to validate thresholds against documented landslide inventories. Okay, then we can move to the methodology part of this research. According to that, first explain about the study setting. Actually, Ditwah has affected for whole Sri Lanka, but especially create critical situation in highland areas. So we have concern about three main Divisional Secretariat Divisions called Ganga Ihala Korale, Uda Palatha and Kothmale for this research as the study area. There are two main data collection parts. We have considered for the research. The primary data collection part goes as field observation, we went landside locations and getting locational data for verification for the data collection of the secondary database method. Then there are several secondary data sources for monitoring rainfall data. We have captured CHIRPS data and analyzing daily rainfall distribution within the specific cyclone situation, 25th November to 30th November, and identify the peak rainfall conditions. Then create the landslide inventory. We collected data from NBRO data and then identify landslide location and analyze spatial distribution. After collected digital elevation model as the DEM images from STRM USGS data portal to generate slope map and analyze terrain influences. After that, create boundary data, actually administrative boundaries from the survey department data portals for defining the study area. Here is the analytical part of this research. We have collected data sets from both modes, primary and secondary based. Then the main process of that is integrate all data sets, geospatial data sets, into a database. Here, this slide shows the process of integrating high-resolution geospatial datasets into a database. Spatial methodology and the overlay analysis. This is very important part of the research. Actually, first of all, we have collected DEM data, then do the terrain extraction part. From these analyses, get slope gradient aspects as the first output. Then go with the rainfall data that collected from CHIRPS, then filtering and mapping daily accumulated rainfall specifically for the time period from 25th November to 30th within the cyclone window. Then have done the overlay analysis part for superimposing NBRO landslide coordinates directly not to rainfall and terrain maps to isolate correlations. After that, we have done the kernel density estimation for transforming isolated event points into continuous spatial hazard hotspots. Actually, this is the flow that we have done this analysis part. Here is the results of the research. As the terrain extraction, we have created topographic vulnerability map by using DEM image. Here, this is the map that represents the topographic vulnerability. Actually, landslides are not randomly distributed within the area, but we can see clustered location in the study area. So, when we are analyzing this result, the most landslides occurs specifically on 16 degrees to 35 degrees slope. Not only that, the general western slope between 0 to 9 degrees demonstrated the minimal to no slope failures. Actually, but the failures were densely clustered in rugged, dissected valleys of the central and southeastern zones. This is the analysis that created based on the T.M.S.P.K analysis. Here is the precipitation analysis. Mainly we concern 6 days, which happened cyclone to Sri Lanka. After analyzing the data, we have identified the peak rainfall distribution days as 27th and 28th November. The concentration is precipitation centralized heavily in the southwestern and central highlands regions. The main impact of this is prolonged cumulative saturation, rapidly weaken subsurface layers, and destroy soil cohesion. Here is the hotspots analysis via kernel density. The first map interprets the landslide location, how distributes within the study area. Actually, raw points data reveals that slope failures were not randomly distributed across the landscape, as I mentioned earlier. Then we move into the analysis of the kernel density. The kernel density mapping smooths these isolated events into continuous actionable hazard zones. The analysis reveals intense localized epicenters of slope failures tightly clustered within Uda Palatha and Kothmale areas. That is the identification of landslide susceptibility from the kernel density. Here is the formula that we have used for the analyzing of threshold value, and this stage the rainfall intensity duration relationship was modeled using the power law equation, and this study derived the first cyclone-specific empirical rainfall threshold model for Sri Lanka. It's derived the first event-specific empirical formula for a Sri Lankan cyclone, but then capture the highly concentrated extreme nature of cyclone precipitation and demonstrates that exceptionally high intensity is required over short duration to initiate the failures. In the next slide, the graph demonstrates a direct positive relationship between the rainfall magnitude and slope instability. From that graph, we have identified the threshold value as 120 millimeters per day. When rainfall remains below 120 millimeters, slope generally maintain stability. But once rainfall exceeds 120 millimeters, soil shear strength decrease rapidly, causing a sharp increase in landslide occurrences. This slide compares the derived Sri Lankan threshold with international rainfall threshold models. Actually, compared with global models, the Sri Lankan cyclone-specific model demonstrates a much weaker duration dependency but extremely high rainfall intensity requirements. That's the specific part that we have identified from this research. Here is the conclusion and key recommendation for future implementation that led by this research. In conclusion, this research derived the first quantitative cyclone-specific rainfall threshold for Sri Lanka, and the finding confirmed a strong relationship between rainfall exceeding 120 millimeters and slopes between 16 to 35 degrees. So, here's the references part, and this is the end of my presentation. Thank you.